Hi guys, this is the fourth and final video in our equilibrium unit. This video is going to be all about LeChatelier's principle, and this is section 15.7 in your book. In this video we're going to be examining how effects on equilibrium change how the reaction shifts and why that happens. So LeChatelier's principle says that if a system is at equilibrium and it's disturbed by some sort of change in temperature, pressure, or concentration, the system's going to shift its equilibrium position. So it might shift to the left or shift to the right in a way to counteract the effects of the disturbance. So LeChatelier's principle is very qualitative. We're looking to see if we increase temperature, is it going to shift to the left or the right, and why. So, like I said, we're going to be using LeChatelier's principle in this video, but we're going to be using it qualitatively, very conceptual, to predict shifts in equilibrium. Now, the three things that we're going to be looking at are adding or removing a reactant or product, that's concentration. We're going to be looking at changing the pressure by changing the volume, and we're going to look at temperature. And what we're going to look at is we're going to look at how the equilibrium system shifts. As we look at the shifts and as we look at the changes over time, it's really important to know that the equilibrium constant itself, KEQ or KC or KP, does not change. It is constant. What's going to be changing is the way that equilibrium is shifting. Remember that KEQ is always a constant. It's always the same. When we look at changes in equilibrium, we're actually looking at Q. So this visual, I think, is a great review of LeChatelier's principle. It gives each of the three effects that we're looking at, it gives what happens, and it even gives some good visuals. So we're going to start by looking at change in concentration. So if a system is in equilibrium, if we add either a reactant or a product, it's going to result in that being used up. Okay, so if we add a reactant, it needs to be used up to get back to equilibrium. If we remove a reactant, then we need to produce that reactant to get back to equilibrium. Okay, so if a chemical system is at equilibrium and we add or remove a product, the reaction is going to shift so we can reestablish equilibrium. So for example, we have the Haber process. Nitrogen and hydrogen makes ammonia. If H2 is added while the system is at equilibrium, we add more H2. Okay, so we add more of this. Notice now we have too much reactant. Okay, because we have too much reactant, we need to use that up, which means the equilibrium will shift to the right. We're going to use up this reactant that we just added, and we'll make more product. System has to counteract this added H2, so it needs to consume this H2, which means it's going to make more product until equilibrium is established. Notice that it's also referring to K and Q. Okay, so just a summary for looking at concentration. If a chemical system, so if a reaction is at equilibrium and concentration is increased, so if let's say we increase the product, that means we have too much product, which means it needs to shift toward the reactants in order to use up that product and get back to equilibrium. And then the opposite is true if we decrease either concentration. So let's say we decrease the concentration of reactant. Okay, well now we don't have enough reactant, so we need to make more. So it's going to shift toward the left, toward the side with the reactants, until it makes more. And then we have change in volume or pressure. So usually what we look at is we look at a change in pressure by changing the volume. So when gases are involved in an equilibrium, a change in pressure or volume will affect equilibrium, only when gases are involved. So if we have a higher volume, okay, so we have a big container, that means we have low pressure. That actually favors the side with more moles of gas. Okay, because we have less pressure, so we need to balance that out by putting more moles in it. Okay, this means it's going to shift toward the side higher number of moles. And so if equilibrium involves gases, then equilibrium will be changed when we change the volume. Okay, so for example, if we decrease the volume, pressure has increased now. Right, pressure has increased. Now, LeChatelier's principle says that because we just increase the pressure, the system has to shift in order to counteract that. So it somehow needs to shift to remove gases and to decrease the pressure, okay, which means it will shift to the side with the lower number of moles of gases. So here's the summary of this. An increase in pressure favors the direction that has fewer moles of gas. Okay? A decrease in pressure favors the direction that has more moles of gas. If a reaction has the same number of moles of gas on both sides, changing the pressure has no effect because number of moles are equal. And then no change will occur if we increase the total gas pressure by the addition of a gas that is not involved in the reaction. So what that means is if we have N2 gas and H2 gas and we add neon, neon's not even in that. That's not going to have any effect at all. As we look at these effects, as we look at LeChatelier's principle, it's important to know that we have to be adding something that's in the reaction that has an effect on KEQ. What has an effect on KEQ? Gases and aqueous solutions. Solids and liquids have no bearing on LeChatelier's principle. If you add a solid, that doesn't matter. Solids don't affect the equilibrium. If you add a liquid, liquids don't affect the equilibrium. Okay, so we're only looking at what actually affects KEQ. And then effective temperature change. So the temperature affects the equilibrium constant for an endothermic reaction. So if delta H is greater than 0, heat can be considered a reactant, right? When it's endothermic, you have to add heat to the system, so heat is a reactant. If you add heat, then it causes a shift to the right because that's like adding a reactant. If you remove heat, that's like removing a reactant and it's going to shift to the left. And then if you have an exothermic reaction, heat is considered a product, right? Heat is on the product side because it's released. So if you add heat, then it's like adding a product. It's going to shift toward the reactants. If you remove heat, that's like removing a product, and it's going to cause a shift to the right. You need to make sure when you're looking at the effects of temperature changes, you need to make sure that you notice if it's endothermic or exothermic. If you don't know, then you can't tell how the effective temperature is going to play a role in equilibrium. So this just gives an example of temperature and LeChatelier's principle. So at equilibrium, we have kind of this violet solution. This is a coordination complex, but we have kind of this purple. If you heat it, it turns blue, okay? Because if you look up here, if you heat it, you have more of the products. If you cool it down, okay, you actually get more of the reactant side because you're removing some of this heat that's on a reactant side. So if you're removing this heat, it's going to shift in order to make more heat, which is why you also get this pink color because that's the other reactant. So at room temperature, the equilibrium mixture was purple. When you put it in warm water, it turned blue because it shifted toward the products. When it's placed in ice water, it turns pink because it's shifted toward the reactants. So, summary of temperature. When the temperature of a system is increased, system reacts as if we added a reactant if it's endothermic, or a product if it's exothermic. The equilibrium is going to shift that's in a way that's going to consume that excess reactant or product. So you always want to think in terms of temperature change, think of it like a reactant or a product, right? How is it going to change if you add or remove a reactant or product? So the effect of catalyst. So a catalyst, the whole point of a catalyst is to lower the activation energy, and we talked about that. Okay, we're going to lower the activation energy of the reaction, and it increases the rate. So this is all about kinetics. So a catalyst is going to decrease the time that it takes to reach equilibrium. So equilibrium is achieved faster, but you're not actually changing what is in the equilibrium mixture. So a catalyst does not affect the composition of an equilibrium mixture. Catalyst has no effect on equilibrium. Okay, so that is it for this video on LeChatelier's principle. What I will be doing is I will be making another video that goes through the examples that are in your notes so you can follow that along. So try each of the examples and then watch the video and just check your answers.